Hi, my name is Madina. I'm a data scientist at SI, and today I'm presenting multimodal person verification with generative thermal data augmentation. Person verification is the process of confirming a person's identity based on various types of biometric data. In this work, we explore speech recordings, visual and thermal facial images. Previously, with the help of SpeakingFaces dataset, we showed that the fusion of audio, visual, and thermal modalities is effective in building reliable person verification systems. In this study, we would like to enhance their performance by augmenting training data using domain transfer methods. We enriched the audio-visual thermal SpeakingFaces dataset with a combination of real audio-visual data and synthetic thermal data from the VoxCeleb dataset. The missing thermal stream is generated using the visual images that are present in the dataset and a visual-to-thermal image translator. On this slide, we present examples of synthesized thermal faces for VoxCeleb. The left part of the figure shows the pairs of real facial images from SpeakingFaces that were used to train our visual-to-thermal translator based on CycleGAN. The right part illustrates the new thermal faces produced by the generator using the real visual images. As we can see in the figure, the generator was able to preserve the key facial features, such as eyes, nose, and lips. The model accurately traced the hairline, but had problems with the eyebrows, when their color in visual images was too close to the subject's skin. The generator was unable to fill in the glass area, but retained the different head postures of the subjects. This mixture of real and generated data were used to train our person verification systems. In this work, we explored 5 variations: unimodal audio, unimodal visual, unimodal thermal, bimodal, and trimodal models. The key part of each model is an encoder that was based on ResNet34 and was responsible for retrieving low-dimensional representation of input data. The result was then transformed into a final embedding vector. In multimodal systems, the transformation happened using soft attention fusion. All models were trained with angular prototypical loss. At the evaluation stage, the models were provided with pairs of multimodal input. The similarity between the extracted and normalized embedding vectors was measured by the Euclidean distance between them. These values can be used directly to make predictions for the model that produced them. The similarity scores can also be summed up with values from other models. A common practice is to take the mean of all scores available for a given data sample and then make a joint prediction. Previously, we have only few scores from unimodal models. Here, we examined 6 variations of score fusion settings that span all modality variants. To analyze the impact of synthetic thermal data on model performance, we gradually increased training data in terms of size and variability. 0% was the training split consisting of only SpeakingFaces. In 1%, the total number of subjects was increased from 100 to 160 by adding a random 1% of training subjects from VoxCeleb. In 5%, 4% of the new random subjects from the VoxCeleb development split were added to the existing 1%. Finally, in 100%, all data from VoxCeleb to development split were combined with SpeakingFaces. In this table, we present the equal error rates on SpeakingFaces validation and test splits. Here we can observe the effect of gradual growth in training data on verification performance. The best performing models were selected based on the validation split of SpeakingFaces. The equal error rate on the test set decreases as we increase the amount of training data for all modality settings. The addition of synthetic data indeed strengthened the unimodal and trimodal models. Among the trained models, the best result on the test set was obtained by the bimodal model with 1.15% of equal error rate trained on the merged real audio-visual data from both datasets. Here are the 6 score fusion combinations of the trained models. In the previous study, we explored only the fusion of unimodal models, where a combination of all 3, audio, visual, and thermal, was better than of the 2, audio and visual. The current results show that the statement holds only up to 5% of synthetic data. At 100% of VoxCeleb 2 trained data, most of the thermal images are synthetic. And the addition of unimodal thermal no longer improves the performance. However, the trimodal models achieves the best performance combined with the unimodal audio, unimodal visual, and bimodal. the higher performance of score fusion technique comes at the expense of the resources required to train multiple models. Here, we present the number of parameters, the training time per epoch, and the total number required for the best models. For instance, the best combination of the 4 models, unimodal audio, unimodal visual, bimodal, and trimodal, trained on 100% of the data, requires 362 hours in total to develop the best performing models. In this table, we present the effect of gradually increasing the size and variability of the training data on the equal error rates on the VoxCeleb test set. The best performing models were selected based on the test split of VoxCeleb 1. Similarly to the results on SpeakingFaces, increasing the amount of VoxCeleb data at the training stage improves the overall performance of all modality settings. The addition of synthetic data indeed strengthened the unimodal thermal and trimodal models. Among the trained models, the best result on the test split was obtained by the bimodal model with 1.6% of equal error rate. Again, score fusion of unimodal audio, unimodal visual, bimodal and trimodal models trained on all available data produces the lowest equal error rate with a mean of 0.81%. We also compared our results on the test split of VoxCeleb 1 with other methods reported in the literature. Instead of mean and standard deviation, we list the equal error rates for all 3 experiments conducted in each category. In each category of the results, the scores of the best performing versions are within the range of other methods. Unfortunately, neither of these works report results with multiple seeds, so it is unclear how robust these techniques are to random initialization. We further evaluated the robustness of our best performing models by simulating suboptimal low-illumination environments using gamma correction. The correction was performed on the test set images of SpeakingFaces and VoxCeleb datasets at a varied power. This way, we recreate gradual darkening of the visual images. Although our results were slightly higher than the error rates of other methods in the field, the evaluation with gamma correction shows how well our models trained on clean data withstand corruption in one of the key sources of input data. In summary, in this work we showed how a generative model trained on relatively small dataset for visual to thermal domain transfer can be utilized on another publicly available large dataset. Also, training with synthetic data produced by this generative method improves the performance of deep unimodal and multimodal models. And finally, the score fusion of unimodal audio, unimodal visual, bimodal and trimodal systems trained on the combined data achieved the best results on both datasets and exhibited robustness in low illumination conditions. If you want to learn more about this work, please check out our GitHub repository. There, we posted our code, pre-trained models, and the pre-processed dataset to facilitate reproducibility and further research in multimodal person verification.